Okay, welcome to the lesson on acceleration. Acceleration is a vector quantity that is defined as the rate at which an object changes its velocity. An object is accelerating if it is changing its velocity. In other words, it's how quickly or how slowly an object changes its velocity. Since velocity has two aspects to it, acceleration can occur under three conditions. Either the speed changes, the direction changes, or both speed and direction change. An object that has a changing speed or direction is considered to have non-uniform motion. Example, a car turns a corner at constant speed. The direction is changing. So if you've ever been in a car that changes direction, it turns, for example, you feel pulled towards the opposite direction of the turn. And that pulling sensation or force is a type of acceleration. You can feel the acceleration. A ball rolls down a hill is another example of acceleration. The ball is speeding up as it moves down the hill, as you just saw in the activity prior. And an object falls straight down, also accelerating because it's speeding up as it's moving downward. Constant acceleration. If an object changes its velocity by the same amount each second, we say that it has constant acceleration. So here are two examples of constant acceleration. So here you have in this table, you have velocity, and here you have time. So after 1 second, the speed or velocity changes to 4 meters per second. After 2 seconds, it changes to 8 meters per second. So it's increasing by 4 meters per second every second. So that is the acceleration. And it's constant because it's changing by the same amount of speed every second. In this case, you're going up from 0 to 1 meter per second, then to 4, then to 5, then to 7. So it's increasing by 3, then it's increasing by 1, and then it's increasing by 2. So the rate of change is not the same. So this table shows changing acceleration, and this table shows constant acceleration. I'm going to leave this analysis of this table for a later time. Acceleration is calculated by the following equation. Acceleration is equal to delta v over delta t, which equals v final minus v initial over delta t, where a equals acceleration and the units are meters per second squared, or also written as meters per second per second. Vf equals final velocity, Vi equals initial velocity, and delta t equals time. So this unit of meters per second squared is change in speed over time. So change in speed is measured in meters per second divided over time, which is measured in seconds, equals meters over seconds, which equals meters per second squared. A change in velocity occurs when the speed or direction of an object changes. Change in velocity can be calculated using the following equations. Delta v equals v final minus v initial, where delta v equals change in velocity, vf equals final velocity, and vi equals initial velocity. Here's a sample calculation. An object is moving at 8 meters per second east, then changes its speed to 3 meters per second west after 2 minutes. Calculate the acceleration. So first we write the given information. V initial is equal to positive 8 meters per second. V final is equal to negative 3 meters per second because it's moving in the westward direction. So the object changes its direction. and delta t equals 120 seconds because we have to convert minutes to seconds. Here's the equation that we use. V final minus V initial over delta t equals acceleration. We plug in our values and we get acceleration is equal to 9.2 times 10 to the negative 2 meters per second squared. And that should actually be a negative 9.2 meters times 10 to the negative 2 meters per second squared. Acceleration is a vector. It has both magnitude and direction. If an object is slowing down, then its acceleration vector is opposite to the velocity vector. If an object is speeding up, then its acceleration vector is in the same direction as the velocity vector. So, for example, let's say you're in a car moving forward. If you're moving in the forward direction, your velocity vector is in the forward direction. And let's say you hit the gas pedal. Then when you hit the gas pedal, you accelerate in the forward direction. And so the acceleration is also in the forward direction. If the acceleration vector and the velocity vector are in the same direction, then the object speeds up. Now let's say you're in a car that is traveling forward. So the velocity vector is in the forward direction, but you hit the brakes. So your acceleration vector is negative. If the velocity vector and the acceleration vector are in opposite directions, the car will slow down. Now, some people think that when the acceleration vector is negative, then the object slows down. That's not the case. It's only if the acceleration vector is in the opposite direction to the velocity vector that the car slows down. So you could have negative acceleration and negative velocity. So for example, if this car is moving in the negative direction, moving backwards, the velocity vector is negative. And if you hit the gas while moving in reverse, then the acceleration vector is also negative, and the object speeds up in the negative direction. Here's a diagram of velocity vectors and acceleration vectors in different times of motion. So while the object is slowing down, the direction of the acceleration is opposite the direction of motion. So here they're in the same direction, speeding up, opposite directions, slowing down. Both of the following are examples of positive acceleration. In the example 1, the object is speeding up in the positive direction. Both velocity and acceleration are positive. In example 2, the object is slowing down in the negative direction. The velocity is positive, but the acceleration is negative. So here, for example, in the first case, you have positive velocity. The velocity is positive and the speed is increasing. So here you would have positive acceleration and positive velocity. In this example, your velocity is negative, but the object is slowing down in the negative direction. So the acceleration vector would actually be positive. So the acceleration is positive in both cases, except in case 1, the object speeds up, and in case example B, the object slows down. Check your understanding. Calculate the acceleration for each example in the table. Pause the video and see if you can try that on your own first. Okay, here's the calculation. So for example, A, the acceleration is v final 8 meters per second minus v initial 0 meters per second divided by 4 seconds, which equals 2 meters per second squared. And example B, the acceleration is 0 meters per second minus negative 8 meters per second divided by 4 seconds, which equals 2 meters per second squared. So the acceleration in both cases is actually exactly the same. What is the direction of the acceleration for each case below? Pause the video and see if you can figure that out. Calculate the acceleration for each scenario. So case A, the acceleration is positive 2 meters per second squared. And for case B, the acceleration is negative 2 meters per second squared. So you can calculate the acceleration. You can also look at it and see here that in case 1, the velocity is positive velocity, and it's increasing, it's speeding up. So the acceleration must be in the same direction, so it has to be positive acceleration. In the second case, look at the velocity. It's positive, so it's positive velocity, but the speed is slowing down. So if the speed is slowing down, the acceleration is always going to be opposite the velocity vector. So it's going to be negative acceleration. And that concludes the presentation. You can try the practice question worksheet.